In this video, we'll be learning how to write out the 6 trigonometric functions for a right triangle. So this topic of trigonometry only applies when we are dealing with a right triangle. So what you should all know already about right triangles is that all of them contain a right angle. Then from there, they all contain a hypotenuse that is across from the right angle, and then they contain two legs. And when you label an angle, so say we labeled this angle theta, that angle has an opposite side leg and an adjacent side leg. Opposite means across because it is across the triangle, and adjacent means next to. So we're going to use this as our basis for studying the 6 trigonometric functions. And of the 6 trigonometric functions, you've hopefully already been exposed to 3 of them. You have sine, cosine, and tangent. And commonly we use the acronym SOHCAHTOA to remember that sine is the opposite side length over the hypotenuse, to remember that cosine is the adjacent side length over the hypotenuse, and then to remember that tangent is the opposite side length over the adjacent side length. So those are 3 ratios that we are already aware of. Now today we're going to add in 3 more ratios. We're going to add in CSC, which stands for cosecant. And essentially all cosecant is the sine ratio flipped. So you'll notice this is hypotenuse over opposite. We then have SEC, which stands for secant, which is hypotenuse over adjacent, so it's just the reciprocal of cosine. And then we have cotangent here, so COT, so that stands for cotangent, and that one is the reciprocal of the tangent function, so now it's adjacent over opposite. So typically what I do is I focus on remembering sine, cosine, and tangent, and then I just remember which one they pair up with. So tangent pairs up with cotangent, and then you just flip it over, so that's pretty easy. And then how I remember these two is because sine doesn't have the word co in it, it pairs up with cosecant, and because co doesn't have the cosine has the word co in it, it pairs up with secant. So notice that in each one of these pairs where we're pairing them up, one of the words says co. So that's kind of how I remember them. They each pair up, and then the tangents pair up together. So in this example here, we're going to evaluate the 6 trigonometric functions of the angle. So here we have this given angle, and we can see we have a right triangle. So we know that the trigonometric functions apply. The first thing I'm going to do is I'm going to label the opposite, the adjacent, and the hypotenuse. So across from the angle is the opposite, so this is my opposite leg. Then 5 is next to it, so that's my adjacent leg. And then here across from the 90-degree angle is my hypotenuse. Now what I notice as I look here is that I don't actually know the length of my hypotenuse. So I'm going to have to calculate that before I can do any of these trigonometric functions. Now what I notice is that because I have a right triangle and I have 2 side lengths, I can use my Pythagorean theorem. So I can use that a squared plus b squared equals c squared function. And so I know that c squared represents my hypotenuse, which is what I don't know. And then I know that each leg, the 5 and the 12, represents a and b. So we have 5 squared plus 12 squared is equal to c squared. So we get 25 plus 144 is equal to c squared. 169 equals c squared, and then we just square root. And while c does equal plus or minus 13 because there are 2 numbers that when squared give us 169, we aren't going to include the negative version of that. We're just going to say that c equals 13 because a side length needs to be positive. It can't be a negative side length. So here we now know that our hypotenuse value is 13. So the next thing I'm going to do is I'm going to find all 6 of my trigonometric ratios. So I like to start with sine. So sine of theta, and remember your theta needs to be in there because that tells you which angle you're referring to. So sine theta, we're going to do opposite over hypotenuse because we have SOHCAHTOA. TOA, and sine is opposite over hypotenuse. So we take our opposite side length, which is 12, over our hypotenuse, which is 13. Now, if you remember which ones pair with which ones, you can immediately just go into and find cosecant because it's just the flipped version of this. So sine and cosecant are reciprocals of each other, so cosecant, if I flip it over, is the hypotenuse over the opposite. Then from here, I'm going to move on to cosine of theta, which I know is my adjacent over hypotenuse, so I have 5 over 13. And then my secant is just the reciprocal of that. So my secant of theta is the adjacent in the denominator and the hypotenuse in the numerator. And then finally, we're going to find tangent of theta, which is opposite over hypotenuse. So I have 12 over 5. And then from here, we're going to find the reciprocal of this to do cotangent. So that's going to be adjacent over opposite, which is 5 over 12. So here we have the values of our 6 trigonometric ratios. So let's try this again with a slightly more difficult example. So here we again see that we have a right triangle and we have our angle theta. We can see that the 7 value is our hypotenuse. We can also see that 4 represents the opposite leg because it is opposite of the angle. And then we notice that we have this side length here that is the adjacent side length, but I need to calculate what it is. So I'm going to start here by using the Pythagorean Theorem to help me calculate that missing side length. So I start off and I have a squared plus b squared equals c squared. Now I know my c squared is 7 squared. I then have 4 is one of my squareds, and then I'm just going to leave the b squared as is. So here this becomes 16 plus b squared equals 49. Subtract 16, we have b squared is equal to 33. So we square root that and we take only the positive answer. So we end up with b is equal to the square root of 33. Now for these, we're going to leave them as simplified square roots. We're not going to use the decimal version because that's not the most exact version. So since 33 is not divisible by any perfect squares, the square root of 33 is as simple as that goes. So here my adjacent side length is the square root of 33. So now I need to move forward and I need to find my 6 trigonometric ratios. So here I'm going to start by finding my sine value. So sine of theta is opposite over hypotenuse. So we can leave that right there as is. And then we do cosecant to pair with that because it's just the reciprocal. So it's 7 over 4, which is hypotenuse over opposite. Then we're going to move on to cosine. So we have cosine of theta. And that is adjacent over hypotenuse, so the square root of 33 over 7. And then the next one is our secant of theta, which is going to be hypotenuse over adjacent. Now, it's not good practice to leave square roots in your denominator, so we need to do something called rationalizing our denominator, which basically means we're going to multiply the top and the bottom of this fraction by the square root of 33. Because it's basically like multiplying by 1. But when we do this, we end up with the 7 times the square root of 33 in the top. But in the bottom, we get this basically the square root of whatever 33 squared is. And because we're doing 33 squared inside of a square root, it just becomes 33 in our denominator. And we don't want to leave square roots in our denominator. So always make sure that you rationalize your denominator with this quick little step. Then finally, we're going to do tangent. And tangent is going to be opposite over adjacent. So again, I notice I have a situation where I need to rationalize my denominator. So I multiply by the square root of 33 on each, and I end up with a tangent value of 4 square roots of 33 over, this becomes whatever 33 squared is inside of a square root. So we have 33 in our denominator. Now for cotangent, I'm actually going to go back to what the original tangent was here. And I'm just going to flip that over to its reciprocal. So we have square root of 33 over 4. So for this third example here, we're essentially going to do the exact same thing, but we are actually given one of our trigonometric ratios. We're going to draw that into a triangle and then find the other 5 trigonometric ratios. So what I'm going to start off doing here is drawing a triangle because I need to have a right triangle in order to use trigonometry. So there I have my right triangle, and I'm just going to place my angle theta wherever I would like it to be. So I'm going to put it in that lower left-hand corner there. Now from here, remember, sine is opposite over hypotenuse. So from this sine function, I can label that my opposite side length, so the one across, is going to be 8 because this is my opposite side length of my angle. And then my hypotenuse is across from the 90-degree angle, so I have 15 here as my hypotenuse. So we have our hypotenuse and our opposite labeled. Now, to find the other side length, we need to use the Pythagorean Theorem. So here we're going to substitute those values in. So I have 8 squared plus b squared, because I don't actually know what this other side length is equal to 15 squared. So I have 64 plus b squared is equal to 225. Then if I subtract 64 on each side, I end up with b squared is equal to 161. Square root both sides, and we end up with b is equal to the positive square root of 161. And we're just going to use the positive version because lengths are positive. So here I had my sine ratio. So I can use sine to help me find cosecant pretty easily because cosecant is just the reciprocal of that. So it's going to be 15 over 8. Cosine of theta is going to be adjacent over hypotenuse. Well, I now know that my adjacent is the square root of 161. So I have the square root of 161 over my hypotenuse, which is 15. I then can find secant because it's the reciprocal of that, so it's 15 over the square root of 161. I then rationalize that denominator by multiplying the top and the bottom by the square root of 161. So I end up with 15 square root of 161 in my numerator. This bottom becomes the square root of whatever 161 times itself is, so that becomes just 161. Then tangent of theta is opposite over adjacent. So again, I need to rationalize my denominator here. Multiply both by the square root of 161, and that just becomes 8 square root of 161 over 161. And then cotangent, I'm going to flip this original of tangent here. We have square root of 161 over 8. So for these ones where they give you values, you need to draw a picture of it so that you can then find your missing value. And then it's the same process as before. You use your knowledge of what the ratios are, using SOHCAHTOA as a reference, and then flipping to the reciprocals for the other 3.